So welcome to another lecture for Computer Science 2A on binary I/O. So what we're going to have a look at is we're going to look at doing input and output now using binary instead of text. We looked at text files, we worked with a scanner and a print writer, and we could write that data to a file. We could open that file, read the contents because it's a human readable text. We could access it very easily. However, that's not the way files actually work. The files, just like anything else on the computer, is just ones and zeros. So instead of writing text, where text is something that is a conversion from ones and zeros into something that we as human beings can understand, we're going to write pure ones and zeros to a specific file. Now, it doesn't make sense to just write pure ones and zeros unless you know what occurs at what location. You can say, for example, the first 8 bytes might be something. The next 8 bytes might be something. The next 24 bytes might be something else. You have things known as file formats, which dictate what occurs at what location and how are they actually formed. Now, in order to work with those types of files, we need to understand how Java works with binary I/O. We'll talk about binary I/O in the bigger picture, and then we'll talk about it in the Java context. We'll have a look at a few different classes that are involved with I/O in general. Some of these classes you will be using again when you get to Computer Science 2B, when you work with network streams. They'll be important there. You'll also be communicating over a network stream with binary I/O and sometimes also with text, depending on the protocol that you are using when you do network communication. But for us now, specifically, we're going to look at doing it with files. So with binary I/O, we're working with reading and writing on a byte level. Byte level, what is a byte? Byte is consisting of 8 bits, each bit either 0 or 1. Now, most of computer systems we work with is working with either mechanical drives, so hard disk drives, or it's working with solid-state drives, SSDs, or flash drives, which are also solid-state systems. We don't work with the very old format of vacuum tubes, and that's how they used to do it. A vacuum tube could either be have a vacuum or not, and that would be the state of a 0 or a 1. Now, when we're working with those types of disks, we're starting to touch on working with a computer on a lower level. When you're looking at a computer or any computing system, you have things like the CPU, you have things like RAM, and you have things like storage, which will be your hard drive or your SSD. All of these things operate at different speeds, and that's going to be important when we talk about working with files in just a moment. Now, with reading and writing, usually there is some encoding format that is written when you read and write files. When you're using a specific file, a specific encoding format is used. Now, depending on the type of file you're working with, depending on the operating system you're working with, those can change. And the encoding format basically is a way of saying that these many bits or these many bytes mean something specific. You need to count 8 bits or 1 byte, and then you translate that 8 bits into a meaningful character. For us, our purposes, when we work with text, those textual characters, the characters that you see in the actual text file, each one of them take 8 bits. Each one of them have a unique 8-bit representation. And we need to convert from the 8-bit representation into something that we can see as human beings. So if I have to look at, for example, any file that you have, if you're looking at this file, you can see specific characters. You can see the characters REM there on line 1. But what is actually written on the disk itself? For that character R, there's a certain bit sequence that represents the character R, and that is what is present on the actual disk that is involved. At the moment, what actually is happening is because we're running this in an application, it's ready from disk into memory, and then from memory onto your screen. All of this, memory, screen, CPU, all of that, you'll learn more about that in Computer Science 3B. But for now, we're just interested in the fact that what we see is an encoded format or decoded format of binary that's written on the actual disk. So when we have text, we have to convert. When we write text, we have to take the text, convert it to binary, write the binary. When we read text, we read the binary, convert it to text, get the text out. That conversion takes time. That conversion takes space. We could write more efficiently by avoiding encoding altogether, just writing raw bits. Instead of writing the character 10 to represent 10, I can write the binary value of 10 to disk, and that will use a lot less space. Instead of 8 bits for each character, I can store it in less than a byte of information. There's also a concept called idionness, and I'm not going to talk too much about that, but that is something that's important when we deal with low-level machine code, and it has to deal with where is the higher bit stored and where is the lower bit stored. That's something we'll cover more when you get to Computer Science 3B. Now, in terms of working with bits, there are a couple of classes inside Java which can work with binary streams. So all this, again, remember, object is our ancestor class. Everything comes from object. But there you can see there's two streams, an input stream and an output stream. This is not system in and system out. System in and system out are input streams, but there's a larger abstract class higher in the hierarchy, and that is input stream and output stream. Now, this is obviously not the full hierarchy of those two classes. This is just a subset for whatever we're going to look at. But if you see there for input stream, we have something called file input stream. So that specifically deals with files. Then we have something called filter input stream, and it has a couple of subclasses as well. And then we have object input stream, and that looks at working with objects in some way with binary data. Data input stream and buffered input stream, those are going to be types of filtered input streams, and we'll have a look at that in just a moment. Now, for every input stream, you have an equivalent output stream. So one getting information, one sending information, depending on where you want to use it. Either a file, coming out of the file, going into the file, or it could be a network stream. It could be the console, just the system in, system out. It depends on what you want to try and do in that specific situation. So usually there is an equivalent way to get data in and a similar way to get data out. So let's look at a file output stream. So file output stream, we want to write binary data now to a file. So this is one of the places, actually all the code I want to change in the slides because they're not using automatic resource management, and I want to change it to use automatic resource management. I'll show both, but slides at the moment only have one. So I'll update the slides and then you'll have both versions available. So here we have a file output stream. We want to write data. We're going to write to a specific file. Now, because we're not using automatic resource management, we have to declare our output stream outside of our try block, initialize it in the try block, and in the finally block, we can try and close. Now, there's something interesting going on with the close here. So not looking at how to write the file just yet, but if we look at the close, you'll note that in the process of trying to close, so first we've got our null check to check if our stream is actually available. Can we close this thing? If it's not null, that means it's available. We can try and close it. But in the process of trying to close it, an exception can occur. So this is different than what we saw with the print writer and the scanner that we had before. We closed them, no issues. We didn't have to worry about anything. But when you're working with binary streams, you have to handle exceptions when you try and close as well. Now, if we're doing automatic resource management, that will be taken care of for us. However, when we're doing it with manual closing, then we have to handle that. Now, we can't go into another finally section here because the thing we're trying to close has a problem. We can't go into finally and try and close again. It's not going to work. So there's only one set of try catches inside of our finally block. Most of the time, when we're working with files, this won't be an issue. Most of the time. Same way, it's not an issue that you don't have the correct permissions. Usually, the files and folders that you're working in, you have permissions to read and write, so you don't have issues with that. Where you will see this become a problem, when you try and close a stream and it doesn't close correctly, is when you start working with network streams. So again, when you get to Computer Science 2B, that's where you'll see this become a very important part of what you're trying to do. Okay, so let's go and look at how do we actually write a binary file. So here you can see we initialize on line 5, file output stream. We pass the file handle as a parameter. Obviously, we need to write to a specific file. We need a file handle. And then we have a for loop, line 6, 7, and 8, 6 to 9. And there you can see we have write k. So that write method can take in integers, or more specifically bytes, and it writes a byte at a time. So it's going to write the bytes 0 up until 9, 10 characters, 10 numbers, actually, not characters. Now, what's interesting about those 10 characters, if we try and read it with a text editor, something that understands text, it's going to read those digits out of that file in that sequence, but it won't understand what it is. It will give us the correct information, and we'll see that in a moment. So after we're done with that writing, then we're essentially done with the writing part. We have our cache block, we have a finally block, and we're done writing the file. If we look at reading the file, it's going to follow a similar structure to what we had with our scanner. We have to keep reading the file until we're at the end of the file, or in this case here, we keep reading the input stream until we end at the end of the input stream. So again, we initialize our file input stream outside of our try block, and then in our final block we close. We might have an exception when we close, so we've got another try catch there. And then we have a while loop, and this while loop reads in a value and tests the condition all at the same time. So you can see we have a value equals input.read. The result of that will give us a number, and we compare that number to -1. -1 in this situation means that there is no more data to read. We're at the end of our stream. At the end of our file input stream, we're at the end of the file. There's no more information left in our file. So we keep reading out of the file, and we're reading byte values. Read a byte value, read the next byte value, read the next byte value, all until we reach the end of the file, in which case read will return -1. Once we reach -1, we know we're at the end, and we can exit perfectly fine. What are we doing with this value read? We're just going to print it out. We're just going to show that we can read that value out, and that's all that we can do. We can only read and write numbers, specifically bytes. Now, in terms of what you know so far, is this useful for you? Reading and writing bytes. Can you understand how to write and read different bytes to interpret different information? I don't think so. If you do, good for you. You can try and do it like this. But for everyone else, we have to work with something a bit more interesting. Most of the time, when we're reading and writing information, we're reading and writing primitive data types. How would you write a float using this? You can only write bytes. How do you write a floating point number only using bytes? For a string, you can sort of figure it out. You can take each character of the string, convert it to its byte representation in the ASCII table, and write that byte. But for a floating point number, that things get a bit more complicated. If you want to find out how, I'll see you in Computer Science 3B next year. We do that. Now, if we look at the contents of our binary file, what does it actually look at? So if we go back to our example here, we are writing a file called binfile.dat, and we're writing the sequence 0 till 9. For loop writes 0 till 9. Now, if we open that file in a text editor, what do we see? We'll see, depending on which text editor you open in, you might see nothing, or you might see these funny characters. And if you look at those characters, you might not know what they are. But if you know the ASCII table, some of those might be familiar. The first byte we wrote was 0. And 0 in the ASCII table is null. That's the first sequence there. So even though we aren't able to read it, depending on which text editor you're using, in this case here, Notepad++, it's able to understand those specific sequences. And if you look at the ASCII table, that's the first 9 sequences in the ASCII table, the first 9 bytes that are available. Now, obviously, this doesn't make sense to us. That's why we have to have a read method. And if we read it, then the output we'll get is 0 to 9. Because we can understand 0 to 9. We don't understand those ASCII values. Now, this is going to take a lot less space. And we'll see when we run the code for this in the tutorial. When we write this file, it's going to be a lot less space than writing the characters 0, 1, 2, 3, etc. It will take a lot less space. Now, there will be certain situations where it might look like it's taking more space, but we'll talk about that when we get to that situation. But most of the time, writing pure binary is a lot less space than trying to write it in a textual format. Writing binary information, we can also write other information. For example, if you're writing text that needs to be at a certain font size, a certain color, underlined, bold, italicized, all of those different things, we can write that information as part of the file format. And whichever program can read that file format can then show you the correct output. So that's where you have different file formats, and not everything is text, because we have other information that needs to be stored with that file. So writing bytes isn't good enough for us. We need something better. We want to work with binary files a bit easier, and that's where we can start looking at filtered I/O. So with filtered I/O, what we can do is we can use a different type of input stream, something known as a data input stream or data output stream, and we can start working with primitive types. Primitive types being things like ints, doubles, floats, booleans, strings. We can write those types using a data input or read it with the data output streams. Read with in, write with out. Now with this, there is other methods that are available. One of them is called available, and that returns the number of bytes that are remaining in an input stream. And we can use this to avoid an end of file exception. So end of file exception, EOF exception, that means we reach the end of the file. There's no more information to read. And usually if we try and read beyond that, that's when end of file exception occurs. Now, looking at the last bullet point there, I mentioned that when you're working with a computer, you have the CPU, where things are processed. You have memory, where some of your program lives, and then you have the hard drive. Usually that's where your files exist. Each of those operate at different speeds, the slowest being your hard drive. So when we're reading and writing information, it's a good idea to have a little bit of a buffer. What is a buffer? A buffer keeps data around for a while until the buffer gets full, and it writes that buffer in one go. Instead of reading and writing as it comes in, write 1 byte, read 1 byte, write 1 byte, read 1 byte, it waits for 4 or 5 bytes, writes 4 or 5 bytes, or reads 4 or 5 bytes. So this will make that accessing the file a little bit easier. It uses the hardware correctly. Your operating system does things to make this work as well, but we can write code to make use of the operating system's ability to use the hard drives and memory correctly. So anytime you're working with a file, you're always going to wrap that file stream in a buffered stream. And what do I mean by wrap? I mean that when you create your file streams, you're going to have to put them into another type of stream. So here we have a way that we want to write something. We're going to write with a data output stream. But in order to create this data output stream, we're actually going to create some temporary streams in between. Temporary in the sense that we're not going to use the variables. The streams exist all the time in memory. We need a file output stream because that's what we want to do. We want to output to a specific file. Because we might be writing a lot of information or working with a slow hard drive or working with hardware that might not be the same speed as memory, we're going to use a buffered output stream. So the buffered output stream takes as a parameter another input stream. In our case, that's where we're going to put our file output stream. So here you can see I'm taking the parameter of my file output stream as the parameter for the constructor for the buffered output stream. Then we take it one step further. I don't want to write bytes. I want to write primitive data types. So I take my buffered output stream and I put it into a data output stream. Now what happens is when I write something, what's going to happen? If I say data out, write something, it's going to write an information. That's going to write it to the buffered output stream. That's going to write it to the file output stream. That'll write it to my file. So it goes through the different levels and will eventually get to the file. How it does that, not important for us. All we need to know is order that we put it in. That's the order in reverse it's going to take to actually get to the actual file. So with data out, I can write primitive types. So here we have UTF. So UTF is a specific encoding for a string. And there you can write out a string, whatever string that may be. In this case here, we're writing out a name. And then I can also write out the double value. So write out whatever double value you want. You could write booleans, you can write integers, you could write whatever you want, as long as they're primitive types. So far, nothing in terms of reference types. If I have an array, out of luck, because it's a reference type, I can't write an array directly. If it's an array of integers, I could write each integer separately. But then I need to remember, I need to write the size of that array so I know how many integers to read as well. So with binary, there's no automatic thing that happens. We have to remember to read things at the right location, remember to write things at the right location. And then again, we have a situation where if we try and close, there can be an exception that is thrown. Note, however, we only close our data output stream. We don't close every stream. Because what will happen is when we close data out will close our buffer, and our buffer will close the file. So it'll close it in reverse order as well. So we don't have to close all of them, we just have to close our outermost wrapper, our topmost stream that we're working with. Similar for reading, it's going to be the opposite process. Instead of an output stream, we now have an input stream. And again, I have my file input stream, going to read in the file, buffer the file input stream, then data the buffered stream, and then I can start reading primitive data types. The order in which you read must match the order in which you write. If you wrote a string first, you have to read a string first. If you wrote a double second, you have to read a double second. If you read it in the wrong order, it will interpret the bytes incorrectly and you'll get the wrong information coming out, assuming it doesn't crash. There can be an exception being thrown where it tries to read something, it doesn't make sense, and then an IO exception will be thrown. So we'll get to this part of the code, and obviously you won't be reading the file correctly. So in that case here, we're just reading the string, and then we're reading the double, and then we're just outputting that onto the screen. Now, I said reference types aren't available. We can't use reference types at all, unless we use something called an object input or an object output stream. So if we want to write full objects, maybe we want to write, for example, those student instances or the module or the degree that we're doing in our tutorial. If you want to write that to file using binary, if we had to use a data output stream, we could do it. We could write the string, we could write another string, we could write a character, we could write an integer, and then remember to read it in that order. Or we can just take a class and just write that class, that instance, to file. It will take all the different pieces and write the pieces to the file, assuming we follow some rules. So an object input stream, object output stream can handle serialization and deserialization of objects. Serialization, converting that to a serial stream, a single stream of ones and zeros. It's similar to how when we wrote text, it converted each character into binary. Same thing is happening now. It's converting that object to binary and then back again when we read it. So object input stream, object output stream can read and write objects and also primitive data types. So it does both data input stream stuff and object input stream stuff. Now, one thing that has to happen, we have to follow a rule, and that rule is when you want to have an object be written to a file, its class has to implement the Java IO serializable interface. And you'll see that it says something called a marker interface. A marker interface is an interface with no methods. There's no methods in that interface at all. There's nothing for us to implement. But what it allows us to do, we're marking that specific class, and in subclasses that it implements that interface is an instance of that interface. Other conditions, if we want to serialize an array, if we have an array of something that we want to write to file, the elements of that array have to be serializable as well. Primitive data types, by default, are serializable. But if we have an array of students, or we have an array of exoplanets, or we have an array of whatever, they have to be serializable for the object input and object output stream to work. Other rules that we have, we can specifically make things not serialized, make them not write to file. Static data, we cannot change that. Static data cannot be written to file using an object input stream, because objects we're writing instances, static belong to a class. We cannot use that at all when we serialize. If you want to prevent a specific instance variable from being written, there's the transient keyword that we can use to stop serialization of that specific instance variable. Anytime we read and write something, there's always going to be a serial ID that is written as well. This serial ID is important. It keeps track of when you write an instance. If we try and write the same instance again, it will say, okay, I've already written this before, and just reference the earlier version of it. So if we don't write the same thing over and over to the file. So here is an example of a serializable class. You can see there it does implement the serializable interface on line 2. Then we have a static variable, and note, because it's static, it's not going to be serialized. Then we have a transient instance variable, also not going to be saved when we save this specific instance to file. But there we have an array called state, and that will be the thing that will be stored in the file itself. So here, next to two sections of code, it's going to be first writing an instance of a class and then reading that instance of a class. So writing, we're going to follow the same procedure as before. Object output stream, we need to create an object output stream. How do we get an object output stream? We first need a file output stream. We need to buffer that file output stream. Then we need to create our object output stream. With our object output stream, we create an instance of our class and then write that instance to the file. We have our usual try, catch, and finally section. But the most important thing here is we're working with object output stream. If you're going to try and read, same story as before. Object input stream, create a file input stream, buffer my file input stream, create an object input stream out of my buffered stream. Then we have to read. Note here, it says read object. Doesn't say read storable, storable being the class we want to serialize. It says read object. Now, here a couple of things can happen. If the object we are trying to read is not in the class path of our currently running program, we can get an exception being thrown, class not found exception. Because we need to know what the class looks like in order to read it from the file. Now that's not a checked exception, that's why we don't have a catch here for that, but that can happen. But if we have that instance variable, we still have an object, we need to convert it. How do we convert it? The same way as we did before. Check if it's an instance of the thing we want to convert to, and then convert it to the instance using casting. There will be a different way of doing this in the updated version of the slides. I'll show you the new syntax where we do the cast at the same time we do instance of. Rest of the file, the method is exactly the same. Got our catch, and finally, and close. So with this, we can move away from working just with text files. Text files are nice in the sense that we can edit them with any sort of tool. We can open them up in the text editor, and we can edit them perfectly fine. You could use Notepad++ for any text file. It doesn't need to be any text file for a specific program. Any text file can work. But if you want to try and save information that is going to be in a more compact format or more information, maybe something that the user shouldn't edit, usually we go to binary formats, binary information. Sometimes companies will create proprietary formats. What that basically means is they don't tell anyone else how that file actually works. And you need their software to open that file. A lot of companies do this. You only can use my software to open this file. You have to buy my software for $100 a year. Otherwise, go look for something else. That's how they keep you to their system. That's how they keep their algorithms, their way of storing information secret by using binary information. There are some very clever people in the world that will go and poke at that file and try and read bits at a time and try and figure out the file format. That's why you'll see older versions of programs do have open source tools that can convert files, but that's not an easy process to follow. So with this, we can write now binary information using bytes, primitive data types, and objects. So you can expect in your future that's exactly what you're going to do. There is one other file type that we can work with called random access files. If you did Informatics 1, you might have used this type of thing. I don't remember you doing it in so much in computer science, but if you have records and you work with records, you'd use random access for that. We're not going to look too much at this, just know it exists. So with random access, you can go to a random location in the file and read a specific number of bytes. And the methods to do that are things like seek, read or write, and get the file pointer. So file pointer tells you where it's pointing in a specific file. The reason why you would use something like a random access file is when you have large files. If you have a file that's 20 gigabytes big, Can you fit 20 gigabytes in memory? Well, if you have a 32 gig machine, maybe. But if you only have 4 gigabytes of memory or 8 gigabytes of memory, you can't fit that file into memory. So you would use something like a random access file, move at a specific location in that file, and read whatever information you want. So there are specific uses for random access files. We're not going to use them at the moment in Computer Science 2A. Okay, so that brings us to the end of the lecture. So that's where I'll stop here for binary I/O. Tomorrow in the tutorial, we'll continue with the canvas, and then we'll also look at working with binary files. If you have any questions, I'll be at the front. Otherwise, I will see you tomorrow. All right, so what happens if you want to read static or transient attributes? You can't. Usually you store that as primitive types, so you'd write that as primitive information. For static, for transient, you write transient to stop that being serialized. So it might be something like a password that you don't want to write to file. So those type of attributes you usually don't want to write to file. That's why you mark them as transient. Okay, so in terms of reading and writing binary, I already talked about that. All right. Okay, so don't see any other relevant questions. Okay, I'm going to end the session.